Yeah.
Ladies and gentlemen, first talk this morning is Peter Rowlands, University of Liverpool, who's going to tell us how to construct standard model fermions. So, take it away, Peter.
Thank you, John. Okay. I have to go back to 40 years or more. Work I've been doing for a very long time, which is the basis of everything I've ever done. And it's a kind of periodic table for physics, which is over 40 years old. And it's a Klein-4 group connecting 4 parameters: mass, time, charge, and space. When I say charge, I don't mean just electric charge, I mean the sources of the 3 non-gravitational interactions. Now, people didn't used to call that charge, but they've started calling them charges. They started talking about strong charges and weak charges, as well as electric charges. And I think I was straight ahead of them doing that. There's also a principle behind this which is also very important in my work, is that the sum total of everything in the universe is absolutely nothing at all. Right, this is the group. This is a group of order 4. And believe me, that group is exact. I've had a very long time to check it out. And that group is exact. The perfect balance between these parameters. The charge one doesn't look like that to start with, but we will find out why. The symmetry of this one is broken, but we will see how that gets broken. It's not broken to start with. It develops into that. That's an algebraic version showing that the sum total is 0. That's a nice, neat diagram, just like category theory. In fact, I'm thinking of doing a category theory version. Okay, and believe me, that symmetry is exact. And I consider that like a periodic table. But not only that, but each of these parameters has an algebra to itself. And as you go up the table, each encloses the previous algebra, incorporates it. So we start off with scale of, when I say mass at the moment, I mean undifferentiated mass, something like the Higgs field. I mean a continuum. I don't mean discrete mass. We'll see where that comes from in a moment. And time is pseudo-scalar, as in relativity. Now this is the interesting one, charge is quaternion. When you take electric charges, you see they have the opposite signs of force to masses, because these are imaginary quantities. Space is a vector, but it's not just a vector, it's a quaternionic-like vector, a multivariate vector. And if you combine these 3, you can see that these are all independent of each other. They're not, that the quaternion in that doesn't go into that vector, it's a separate system. But you can see that these 3, if you combine them, will be a vector space just like space. So we have, in effect, 2 spaces. And you can show that the properties actually come from the algebras. The properties that I did in that table come from the algebraic structure. So we can do it purely as algebra. We don't need anything else. The space is, in effect, a complexified quaternion. That's been a long-standing theory of people like Hestoners and so on. That space is a Clifford algebra, a complexified quaternion. So we can see that the representation, the algebraic representation, is like 2 spaces. And they act like 2 spaces. Only one of them isn't a space in our ordinary sense of the word, because that one has 3 different components which are separate. But algebraically it's a space. So we never see it as a space. And I'm saying the totality 0 principle suggests that 2 spaces effectively cancel each other out. and one is an anti-space to the other. The same information is in each, but differently organised. I call them real space and vacuum space. Also, sometimes called the space that contains the charges, because they're in the vacuum space, the charge space. And that will be relevant to what we do. These algebras don't include the anti-associative octonions. Some people, for example, Geoffrey Dixon, have advocated that one should use the 4-division algebras to create physics. However, I'm just using what I find physics to be, not what I think it should be mathematically. And while he says R tensored with C, tensored with H, the quaternion tensored with O, is what he thinks might be the algebra, I think it's this one. R tensored with C, tensored with H, tensored with H, 2 H's. And so the requirements of physics are forcing this, not what would be nice mathematically. Why do we exclude octonions and not quaternions? Why do we say anti-commutativity is all right, but anti-associativity isn't? Well, I say anti-associativity, when you're actually doing the operation, involves a kind of time sequence. And if you've got anti-associative, you're reversing the time sequence, and that doesn't happen in physics. However, octonions aren't completely excluded, because the 8 fundamental units of mass, time, charge and space can be structured as a broken octonion. It looks like an octonion because you can structure it with 1 real and 7 imaginary. So you can copy it into an octonion structure, but it doesn't quite become an octonion. Now, when we bundle all the algebras together, say this is it, we don't need any other algebra, bundle them all together, what do we get? We get a 64-part group, which is isomorphic to the algebra of the Dirac equation, the gamma algebra. It's a version of Clifford 6-0 or geometric 6-0, the Clifford algebra of a double vector space. And when I bundled them together and I got what looked like the Dirac algebra, I thought, this is a jackpot. This really must be significant. Let's have a look at them. Now, I like to write my quaternions in red and my vectors in blue. And this is the 64 units. What I want you to notice is that it's grouped in 12 lots of 5. It doesn't have to be, but this is a powerful grouping. Because if we take any one of these 12 groups of 5, and this is the one I usually use, but you can use any of them, any one of those acts as a generator of the entire algebra. That's all we need to generate the algebra. Possibly sometimes we need to complexify it, but most of these will generate the entire algebra anyway. And what's more, these, if I take these 5, these become gamma naught to gamma 5 of the Dirac algebra, these 5. So there's a deep reason for choosing this algebra. It's not arbitrary.
Peter, is the J gamma 5 there in that set? Yeah, good man.
Yeah. And this affects the way you do the quantum mechanics, as I'll explain why gamma 5 is important. Gamma 5 is ignored in most textbooks for fundamental purposes, except for doing chirality. So the isomorphs of the gamma, so you've got 12 lots of units. And they can all be constructed from the original 8 units. And it's the same process each time. You take the units of one of the 2 three-dimensional quantities, space or charge, and attach them to the other 5. So you separate 3 out and attach them to the other 5. Let's see how that works, like so. What I've done there is take the 3 red ones and attach them one by one to each of these. And now what you see now is this is the generators of the entire structure, and you can see that this is a broken symmetry for the red ones. This one is attached to a pseudo-scalar, this one to a vector, and that one to a scalar. And this is why the charges don't behave the same way as each other. We've broken the symmetry of the charges. Yeah, in fact, that's an argument I don't want to talk about now, but you need a conserved quantity to do that, not a non-conserved one. And the symmetry works both ways in the 5-3 division. In the first place, when we do that, we start off with these parameters, but these end up different. This one now has the dimensions of energy. This one has the dimensions of momentum, and this one has the dimensions of discrete invariant rest mass. And so we're creating discrete mass now. And I think Wolf was talking about interaction between mass and charge. This isn't quite an interaction, but it's a connection. And it was electric charge he was talking about, as here. Sorry, I need to go forward.
Yeah, you're not in Octonian space.
Sorry?
You're not in Octonian space.
No, certainly not. No, I don't want to reverse the time sequence. So, okay, we now create the generator, so we've got new quantities. And these, E and P and M, are just scalar values of these. These aren't actually the energy, this is just the scalar value. This is the energy, the algebraic unit is the energy. Now at the same time, we're breaking the symmetry of the three charges. So this charge now takes on a pseudo-scalar quantity, that one takes on a pseudo-vector quantity, and that one takes on a scalar quantity. So they behave differently. In principle, they are the same, but they behave differently when we bundle the units together. And this eventually leads to the SU2, SU3, new one, and I've shown that it does. And if you really want, if you're really interested in this sort of thing, you can make this into a 10-dimensional structure, because you've got 5 of one and 5 of the other. And 6 of them are compactified or conserved quantities. Well, I'm not terribly interested in that, but you can do that if you want. Now, we're talking about what the fermions look like. And what we have now is to look at that. And so there are two structures for the fermions. There's one that does the energy, momentum, and mass structure, and there's one that does the charge structure. So that will give us the information about what fermions are. Immediately interesting is that when you put all these together, let me put them all together like so, into this structure here, all the 5 objects, that in physics, what we find is that that object is always 0 when it's squared. It's a nilpotent. If I square that, I will just get E squared minus P squared minus M squared. Einstein's equation. And if we want the Dirac equation now, all we do is simply apply conservation and non-conservation. And I've explained this elsewhere, but I don't want to do it today. And to the first bracket there. So we apply the first bracket to non-conserved quantities, the second bracket conserved quantities, and we get a version of the Dirac equation, and here we're choosing to write down the free particle one. Now notice this is different from the ordinary Dirac equation, because this is basically gamma 5. And the ordinary Dirac equation doesn't have gamma 5 in there. But it's trivial to make the Dirac equation into that equation. You simply multiply by gamma 5 on the left. It's a trivial operation. And I mentioned that the vector units and those of the Clifford algebra, as Heston his very good work did on that. And this is what we mean, that it has a full product like that, not just a vector and scalar product. And this means that we can write momentum in the equation instead of sigma dot p. You can either write sigma dot p or p in the equation. And I more often write p in the equation rather than sigma dot p. Now the key thing is the amplitude is always nilpotent. And although I've written down the equation for a free particle, it isn't only free particles that do that. As we know, the particles are never free. They've always got some potential constraint. And even if you do that, it doesn't make any difference. It's still nilpotent. And that's the key thing. Now, I've derived a version of the Dirac equation, but I don't really use the Dirac equation as such. I use the Dirac operator. I create an operator, and then the constraint is that the operator, whatever it is, including field terms and all that, is obliged to create the only phase that it can do that will create a nilpotent amplitude. So you have an operator which describes everything, then it hunts around for the phase it must have, and then it operates on that phase and you get a nilpotent amplitude. So once you've described the operator, that's it. There's nothing else to know about that system. So it's just an operator. And I'm mentioning that when you add up everything, you get 0 every time you do this. And this is what I think point particle is all about. Point, when I say point particle, I'm saying that it's like two spaces, and the intersection point of the two spaces is that 0 point. Because the norm of that, the Pythagorean addition, e squared minus p squared minus m squared, is 0. So it's a norm of 0 at that point. Now, people often talk about having points in space, but we can't define a point in space because space has got translation and rotation symmetry. You cannot define a point. You can only define a point in the intersection of two spaces. We combine it with anti-space, which has translation and rotation asymmetry. I can't go into that, but it's a very interesting topic. So we could create a hybrid energy momentum space, and physics has been very successful in basing itself on this without knowing it, because it creates a real space and the hybrid space, which is the energy momentum space, which creates our phase space. And interestingly, real space and charge space or vacuum space are commutative. But each of these is anti-commutative to energy momentum space because this is not independent of either. This depends on the two. These are independent of each other, but this hybrid space depends on the two. And what I say is that once we've defined this point particle, if you like, then we've got locality straight away, and Lorentz invariance because we've got e squared minus b squared minus m squared. The c is simply a factor connected with the units. Yeah, I'll just leave that next bit. I'm saying this is interesting. Noether's theorem connects the conserved and non-conserved quantities, and those are fundamental properties of the group. In fact, I found a new version, not of Noether's theorem, but it related to what a previous speaker said. It's about conservation of charge. I found conservation of charge was the same as the conservation of angular momentum because of a Noether's theorem symmetry. But especially interesting is that the conservation of the rotation asymmetry of charge, the fact that they can't rotate the three into each other, they're separately conserved, means that I found that was the same as the conservation of angular momentum. So it's not written down here, but this is very interesting because that SU3, SU2, and U1, the SU3 is really about the rotation, the direction. The SU2 is about the handedness, and the U1 is about the magnitude. And the conservation of angular momentum is 3 conservation laws, separate, bundled together. And those 3 actually create the 3 SU3, SU2, and U1 structures. And I'm saying you're actually creating, for the first time, you're creating this invariant mass by bundling all this together. It's the effect of, it's the effect of charge on space. It's not what I call an interaction, but it's an effect of charge on space. So it's connected with what you were saying. There might be something of that kind. I'm saying the Higgs mechanism interesting, uses a transition from global to local symmetries to create discrete masses. Here we've got translation from the group symmetry, which is global, to the local symmetry of the nilpotent structure, the particle structure. Okay. Now, as we know, the Dirac equation originally used 4x4 matrices, and that obliged us to use 4 solutions for the wave function. And our terms are equivalent to those matrices, so we still have 4 solutions. 2 Fermion, anti-Fermion, 2 for spin up and spin down. And it's trivial in this representation to do it, you just do that. It doesn't have to be that particular sign convention, but once you've chosen one, that's it, you stick with it. And if you want to do an anti-Fermion, you simply put the anti-Fermion at the top and go through the sign conventions of the other ones. Now, we hear a lot about why is there more matter than antimatter? Well, I say there isn't. There's exactly the same amount of matter and antimatter. This is matter, this is antimatter. So one particle has the same amount of matter and antimatter. It's just that the antimatter isn't in our space, it's in the vacuum space. Whereas the matter is in the real space. So we see the matter but not the antimatter, but they're both there. So that's that. Well, lots of things become immediately obvious. In this expression here, everything inside the bracket is local. That follows Lorentzian laws, etc. Everything outside of it is non-local. Superposition, combination states are non-local. And Pauli exclusion is immediate because you can't have 2 exactly the same because they will cancel each other out. There's another way of doing Pauli exclusion, which is the conventional way, and that leads to something interesting as well. We do, I'm sorry, I've not got up to that yet, but I'll do that in a moment. Here, what I'm saying here is, if you create a fermion with all its bits and pieces, all its potentials and so on, from absolutely nothing, you pluck it out of nothing, you would kind of leave a hole in the nothing. And that's what we call vacuum. So vacuum is like a reflection of what the fermion is. So that's the fermion, that's vacuum. They total to 0, they multiply to 0. Combination and superposition are both 0. So the rest of the universe is what we mean by vacuum. I was going to say this one. Asymmetric wave functions are the standard way of doing Pauli exclusion. So let's do them with this. What do I get? I get this. And I end up with this object here. Now, if I've got a cross product between P1 and P2, and that's only non-zero if P1 and P2 are different in direction. It doesn't matter if they're different in magnitude, they've got to be different in direction. In other words, the exclusive information about a fermion is contained only in the direction of this spin vector. It's not contained anywhere else. That's the only information that we have about any fermion. I think I thought that was an extraordinary result. And it took some believing, but I now know it's true. And this is because we've got 2 spaces. So this is real space, ijk blue, and so the direction of that is like the combination of everything in real space. This one here, you could map your k, I, and j, your energy, momentum, and mass values onto 3 axes with those k, I, and j. And the direction of that would be unique as well. So they're both, so that's the real reason for it, like so. So that's showing the duality of the 2 spaces. So the non-zero is creating a singularity state out of the combination of the 2 vector spaces and no other information. So the information contained in the 2 spaces isn't independent. Each is dependent on the other. And I've shown in other talks, I've got a list of things where you should see this duality. So we can transport information about one space into another. And this is very important for particles. because it's all about swapping information between spaces, how we get those. If you want PT and C transformations, easy with this. You just put pre-multiply and post-multiply effectively by the three quaternion operators. If you want to show that CPT theorem, you do it that way, and you end up back where you started.
So your M is the rest mass.
Yes. Yes, it's
And,
not
and E is the total energy.
Yes.
Yeah, okay.
What the bosons look like, now this might be interesting to several discussions of bosons earlier, because this is what I consider a spin. It's got to be, this is the antiparticle boson, particle part. Now whether this means that it's two objects or one object, it's just a mathematical structure for me at the moment. And spin 1 means the spins are pointing the same way. I do this abbreviated form of all the four states. So you can have three types of boson. You can have spin 1, spin 0, or fermion, as in Berry phase, or as in anything that's Berry phase, Cooper pairs, all that sort of thing. Now, very significantly, a spin 1 boson can be massless, because when we multiply it out, we get a scalar quantity. But a spin 0 boson can't, because this immediately zeros. Hence, Goldstone bosons must become Higgs bosons or something equivalent. You can't have a spin 0 massless boson. And another thing we can do is this. Now, many people say that that particles are minimum left ideals, idempotents, idempotents. Well, this is an idempotent, k times all this, k times all this. So if I multiply that by that, it will just not change. You'll just get the particle multiplied by a scalar which you can normalize away. The same happens with j or I in front. It's a trivial operation of the algebra. When I say that, those are three sections of the vacuum. The vacuum splits into three when you do that. Weak, strong, and electric. I think this has got a connection with gravity gauge theory corresponding, because I consider the V vacuum to be the gravitating vacuum. The 1 times is the gravity, or inertia. It's one of those. Now if I do this, I can do this forever. I'm only doing one of these for convenience, well, the first line of the 4 objects for convenience. I can do this forever. And there's another trick I can play. If I put k on either side of something, I switch k that to minus k. So every alternate one will be minus k. But if you do that, then this becomes a boson. This becomes a boson, and so on. Every fermion is its own boson, if you take the vacuum with it. So every fermion is its own boson. And you can apply that to renormalization to remove the self-energy. And I have done. So we don't have any mass hierarchy problem at all. We just get rid of the self-energy term. So these, of course, are annihilation and creation operators. So boson to fermion, fermion to boson. And you can do those to infinity. Series of boson and fermion loops. Same energy and momentum, perfect cancellation. No problem at all. Dead easy. You can reduce it to arithmetic. You can reduce the renormalization of the self-energy problem to arithmetic. You don't need to do it at all. Only in this way of doing it. So the two spaces become important when we look at particle structures. Baryon seen in real space can be seen in real space through the rotation symmetric momentum operator. But at the same time, we've got a rotation asymmetric vacuum or charge space. Now I can do a version of the strong interaction. Here we got 3 identical nilpotent operators, 0. However, let's suppose that we split the momentum between three components, separated in space. It's still a non-local connection because it's only the local is only what's inside, non-local is outside. And what I'm saying is that if we look at that and work out the mathematics, which isn't very difficult, we find it has nilpotent solutions when P is either plus or minus IPX, plus or minus JPY, and so on. There are 6 possible solutions that give you a nilpotent solution. I'll write them down there. When you multiply them out, you end up with this multiplied by a scalar. And notice this has the same structure as SU3. But the interesting thing is that the middle one has to reverse sign. If it's in the middle, the J, it reverses sign. But if we got both signs, we have preserved the symmetry. If we have both signs, it means we have to have both signs of spin to preserve the symmetry. We have to have both left-handed and right-handed. So there's no chirality in the strong interaction. Definitely not. There's no chirality in the strong interaction because you've got equal left and right-handedness. And also, equal left and right-handedness means maximizing the mass value. It means you've got to have a mass value. By the way, there's a lot of money for solving this problem. If anybody wants to propose me for a Nobel Prize for solving this problem, I shan't complain. There's a lot of money in it. And you can see it's an SU3 transition. Colour transitions in it exactly the same way. See, I'm just doing that. When you multiply this out, this stays the same, except that goes minus, and you end up with a scalar. That's just what happens with the algebra. Gluons. Notice gluons have a kind of, when you multiply this out, you get a kind of pseudo-vector, which is interesting. A pseudo-vector. That's what gluons, in my view, would look like. And we see now why gluons don't look the same as other massless spin 1 gauge bosons. They're not the same as W or Z. They're not massless. They're of this form. The massive spin Higgs is of this form, and photons take the massless form is spin 1. So I go back to this. We've got to either do the phase space or the nilpotent structure, or we've got to do the charge structure. Or we've got to do both to really understand them. Now I'm going to try to get to the charge structures. The nilpotent structures are relatively easily done, but the charge structures are more difficult. So what amounts of this weak component, what amounts of this electric component, what amounts of this strong component do each have? Well, clearly, a baryon has a strong component. No other particle does, hence why nobody's ever been able to show the decay of the proton. You can't get rid of baryons because of that. Because it's got a strong charge component, you can't change the strong charge into something else. All fermions have got a weak charge component, all bosons don't have. Simple division. And this is one of the ways. Let me just see if I can work this out. I used those. Let me just try and do it this way. I'll skip the text. This is inertial gravitation. That's 1 times the object. This is the strong. That's I times the object. This is the weak. That's K times the object. That's the electric. That's J times the object. And those vacuums can fit into this structure. And what we effectively get is that one of these phases is active. This is baryons. One of these phases is active at any time. And only that one. So in this one it will be this. Let's suppose the P3 phase is active, then it will be that one, then it will be that one, then it will be that one and that one. And this is what determines the charge structure that we find. So the P term determines which of the 3 components carries an active term. It's quite difficult, but you can get the nilpotence and the charge structures in one object. I'm going to skip some of this text. This one here is, that's what a lepton would look like. It's got all the momentums lined up. The baryons have the momentum components in different places. These are all lined up at once. Yeah, I'll just leave that. It's quite difficult, so I'm not going to go into detail on it. This is another way of looking at it. You can consider this like a rotating vector. The baryon would rotate, this vector would rotate, the strong charge would rotate while the other two stay constant. But the E and the W have to be on different ones, whereas the lepton, they're all on the same one. Now what I want to talk about is, I don't know how that's 63 got it. It should be 64. Fermion structures from the group of order 64. It's certainly not 63, that would screw everything. The nilpotent structure needs only one of the 12 pentads. I showed 12 pentads, 12 lots of 5. So what's the significance of the others? Well, we can actually use them to see what degrees of freedom we can use to construct fermions. So you've got 36 standard model quarks, 12 standard model leptons and anti-leptons, quarks and anti-quark. These can be represented by using the 4 pentad structures. And the only difference between the leptons and the quarks is the vector structures in the quarks represent choices. I'm going to use the OR symbol like that to represent the choices. So let's see. That would be those are leptons. And I'm just going to arbitrarily choose a pentad for each one. This IJK doesn't represent separate ones, that's just one. They're not 3 separate things. Quarks are like that, similar, but these are either or. So you only have one of these at one time. You have all 3 because you have 3 quarks. But you can also reverse the structures. We can invert the structures, and instead of deriving 5-fold structures, we can do 5-fold groups of particles. So you can do 12 leptons and anti-leptons and 36 quarks. So if I go back to these no longer represent they don't represent one particle. Each of these is a particle. If I do it differently, and you can see that will give me certain degrees of freedom, and I'll explain what they are. Plus and minus is the obvious particle and antiparticle. Separate and combined vector terms represent quarks and leptons. Quarks separate, leptons 1. IJK blue for the colours of what, and IJK for the generations. And the reason why you can use these for the generations is that the generations are obviously to do with C, P and T. You violate parity for the second generation, time reversal the third. So you can use CPT to represent the generations. IJK, not in that order, actually in the order JIK is the way of doing it. This is the one that's not obvious. I represents up or down isospin. But when you look at it, isospin, weak isospin is to do with the symmetry breaking over electroweak, which is to do with complexification. So let me write it this way. I could compose the 64 units that way. Quaternions, vectors, complex numbers, real numbers, 1 and minus 1. And IJK, the 3 generations, one is like a Xerox generation, there's no charges there. One represents leptons, IJK, 3 colours. Isospin up, isospin down, particle and antipod. And this is weak, that's strong, that's electric, the way it works now. Yeah, I'm just saying what the transitions involve, that's quite interesting as well. Because transitions between quarks involves pseudo-vectors, just as the gluons do. Isospin plus or minus, transitions between generations involves quaternions. Creations of firms from the 0th generation also involve quaternion units. It's interesting that quaternions, look at this. This isn't right, this is not quaternions. Oh yes, that's correct what I've said. There's 16 components with no quaternion, therefore no charge. And so there are elements of space or time and mass which don't involve charges. And we know that charges are not present everywhere, whereas mass is. Mass is a scalar, it's included in all 64 of the elements and it's everywhere. It's a component of everything in one form or another. So these symbols don't represent fermion structures, they represent a way of constructing fermion structures from them. What are we up to? I've developed a single equation for doing this. It's a bit complicated, but it's not as complicated as you think. Imagine that this is sigma z, and you're taking the dot product with unit vector directions, and these are arbitrary. Each of these revolves arbitrary. And if you revolve those arbitrary, you get the charge structures. And this is what the strong interaction does, that's what the electric interaction does, that's what the weak interaction does.
So ABC are 3 triple and right-handed.
Correct. Yep, and you could, they're independent of each other, they can be any of X, Y, Z, or 1, 2, 3.
Beautiful.
And so, I'll just skip the detail because it's complicated.
Peter, quarter of an hour, 10 minutes if you want to have 5 minutes for a question.
Yeah, that's fine. That's good because I can skip some of this, the detail. And if I work them out, I get that. If I choose all the possible A, B's, and C's, I get that. Okay. And if I then carry on with those, I get those. Now I had these tables decades ago, but didn't know how to derive them. But now I derive them from algebra. But I'm not going to go into that either. What I'm pointing out here is that I don't use, in the first instance, I don't use fractional charges for quarks. No. And I say that the reason why we see fractional charges is because we've got perfect gauge invariance for the strong interaction. Shaking your head.
We don't see fractional charges.
No.
That's just an interpretation. You can't measure it.
Right, okay. I'm saying, yes, okay. But what I'm saying is that we do get fractional charges, but only because of the perfect gauge invariance is strong. So exactly the same as the quantum Hall effect, where you see charges of 1/3 of the electric charge because one electron is simultaneously on 3 flux lines. So you get 1/3 of a charge in each, even though we know there's no such thing as 1/3 of a charge. Another way of doing it is to use the basic units of IJK, of E, P and N, and take these charge structures. And when you do this, the traces turn out to be the nilpotent structures. There's various tricks you can play. So, there's another question we might ask. Can we get all the fundamental particles in a single group? Well, you can get them in a group, but it won't be a single group. It'll be a broken one. I'm saying here that the only numbers that matter are 2 and 3. You can construct a table of numbers. Let me do it here. I'm going to go straight to it. That. You can construct a table of numbers where you just build it up. And you can do it in any order you want. So probably isospin should come before spin. You've got 4-factor two dualities because you've got 4 parameters. You've got 3 generations, and you just build up your particles here. This is the standard one, 48 fermions, and 12 bosons. And if you can put bosons and fermions in the same table, as has been done, then you end up, if you take all the 48 fermions, and then you take spin up and spin down, you get 96. For every fermion, for every 4 fermion, there's a boson. So there'll be 24 bosons with those, that's 120. And if, you know, in my interpretation of vacuum, you've got vacuum particles that you never see, then you've got 240. That's one argument for getting 240. I don't include Higgs boson in this because it's not a gauge boson. Don't include the spin 2 graviton, which I don't believe exists. And I have, there's a spin 1 inertial pseudo boson, I don't include that either. Okay. So I'm just going to skip over the details of that. So I'm just getting now down to the conclusion. I'm saying the interesting thing about this whole idea is we can follow through many of the fundamental algebras derived from real and complex numbers, quaternions and octonions. Geometries in space from 3 to 8 dimensions and many associated groups. All the key numbers for those, you take anything you want. Kissing numbers, platonic solids, any of those. They all appear in that table. All the numbers, the number of faces, the number of vertices, the number of this, that, the other. Any number of dimensions up to 8, you get the same numbers. Time and time again, made up out of 2 and 3. So we can see complexity building up from the simplest symmetries. There's only 2 numbers that matter, 2 and 3. 2 for duality, 3 for anticommutativity. And that's it. Nothing else matters at all. And that's it. Thank you.
More of a comment. I think it's important for the looming paradigm shift. I appreciate Castine's remark that space-time is a complex tessellation of quaternions, but I feel that that's only to the semi-quantum limit for the standard model, and after that we will find, with the addition of Kaluza-Klein cyclicality and M-theory, that octonions will be required, and there's more to say on that. And just the one comment now, Peter's worry about time. If with Kaluza-Klein cyclicality restricting in terms of the Wheeler-Feynman-Kramer transactional interpretation with the present as a standing wave of the future past, of course, not a one-dimensional, but a Kähler manifold type dimensional structure, the restriction on time is just like the Zitterwegen in quantum theory, annihilation creation, so there's not a concern about time once the cyclicality is.
I don't have any concern about it.
No, you said you did.
No, I'm not about it at all. Sydney.
I was going to ask, I noticed that when in this formalism, when you do the compactification and you do the, I noticed that when we had the phase, it becomes a single, you change the sign variation to a single.
Oh yes, well I didn't do it in this.
No, what I was going to say is, so when you all your slides, you had just the amplitude term, which is important because I was going to ask, when you start going, was the phase that sort of took the back seat?
Yeah.
And then the phase inside the bracket?
Yeah.
Was that, could you say that the phase that took the bracket out, the non-local phase?
Yeah.
Is that, would that be a good way to look at it, that the non-local phase?
The phase is non.
But the phase inside the bracket does all the action with
yeah, that's correct. The phase of
the P. Okay.
In the Nilpotent structure, you say that there is a separation of local and non-local.
Oh yes, indeed. Yeah.
Is non-local equal to global or not?
Global is what we have in that parameter group before we create. Yeah, in a sense, it is global. Yes.
And physically, what means nilpotent structure.
It's Pauli exclusion. The first thing is Pauli exclusion.
Yes, I noticed that.
Because as soon as you've got nilpotent, what it means is that you're separating out a system from the rest of the universe. And then, so that the rest of the universe looks like it's in reverse.
It's a separation.
Yeah.
Yes, okay.
This will fit in very well with your oscillators, this.
We can speak about that.
Yes.
And well, in all your equations, you speak about the penta. Is you have the energy, the speed, momentum, and the mass. And when you speak of the charge, where is the charge in your equation?
The Ki and J are charges.
Pardon?
The Ki and J are disguised charges.
Quaternion.
The quaternions in the equation are the disguised charges.
Repeat.
The quaternion units, Ki and J,
Yes.
are disguised charges.
They multiply the operator of energy, mass, and...
They create the energy, and they create the momentum, they create the mass, because the energy, momentum, and mass are like a combination of space and charge.
Because it means that it's the energy, there is also the energy with charge.
Yeah, that's inside it. But you can fiddle out what the charge structure is as a separate issue.
Yeah.
But you know the effect of the charge is in the energy, momentum, and mass.
Okay, thank you. How?
Does nilpotency mean there's nothing there, or there's nothing
No,
outside
yeah.
of what's there that affects what's there?
No, it means that the total is nothing. Nothing at all, but we're always inside it. Now we're talking about being inside it. We're always inside it, and therefore we can't see that it's nothing.
It's like an instance equation equals to 0.
Well, I like to think we were here.
Yeah.
Weird.
But I'm perfectly willing to believe that there's no angel Gabriel from outside to come in and fix what we're screwing up.
It's just the same as saying f minus ma equals 0, for example. You get that instantly as an operator.
Yeah.
Nil is nil.
No, but f is ma.
What?
Well, nilpotent isn't a
It
nothing.
doesn't mean to be.
It's a square root of nothing. It's not nothing in itself. It's got to be squared to get nothing.
Yeah, but then it has nilpotence. That's even worse.
That's because, I think you're saying like the x is non-zero.
I think it says nothing that's on the outside is affecting what's on the inside. There's no relation. It's a sealed
What to you is the most important physical results
Oh,
were obtained.
there are quite a number.
Being obtained in the frame of your general theoretical.
There are quite a number of those. I'm not able to go into all of them today. I mean, I've made various predictions. I mean, for example, I know the reasons for a lot of things now, like why doesn't the boson decay? And I say it won't ever. That's one example, but there are many. I can get grand unification of the Planck mass with these ones and zeros. And not only that, but I can predict, how the alphas will change over with energy in a way that will be different to what anybody else would predict. Especially the electric one. There's about an 8 or 10% difference from what anybody else would predict. It's open to investigation. There are a lot of others, but I can't really remember those.
So I really like this vision of something separated out, generating a thing, and an absence of the thing,
Yes.
summing up to a nilpotence.
Yes.
But that still leaves you with the something being something.
Oh yes, the something is
And
there.
so what can you describe that?
Well, I can explain a nilpotent very easily. Right, I'm going to walk 4 meters in this direction. That's 4 meters, right? I'm going to walk 3 meters in this direction, and I'm going to roll back to the diagonal, back to where I started. Now, I'm back where I started, that's 0, but I've actually done something. So I can represent that as a nilpotent. Anything Pythagorean can be represented as a nilpotent. So I can write ik5 plus I4 plus J3 squared equals 0. So I can actually describe what I've done, even though I've ended up back where I started.
Anything on the light cone in relativity, for example, is nilpotent.
Yeah.
Doesn't mean light doesn't exist.
Nilpotent
It means
is...
you can't resolve it.
Oh, it means it squares to 0. That's all it means.
That's all
No,
it means.
it means you can't resolve it. You can't tell. If you get a signal on the light cone, it could be from something far away, long ago, or it could be something close by recently. The two arrive together, so the observer can't resolve it.
Well, we can argue about that, and I will in a minute, but not just now. May I ask a quick question as well? It's beautiful, the structure that you have with these three-dimensional space or two three-dimensional. We're talking about something which is a place in space. How do you bring in, or would you bring in relativity to
It is relativity, because it's e squared minus b squared minus m squared. It's already relativistic. It's automatic. Relativity is
So
automatic.
you've got relativity built in at the point where you come in.
Yeah, it's automatic. It's automatic
Yes.
because you've got this squaring to zero.
Okay, so all I always read.
So it's automatic.
Peter, stay here.
Right.
Is Albert Minkovic here?
Okay, it's in the
Albert Minkovic?
Thank you.
It's wonderful. Sorry.
No, I'll not stand in the way of the next speaker. Just
Hector, are you ready to take it away? Of course, it's right on time.
How will you get some water for you?